Hey everyone, this is Daniel from PV Prep, and today I'll be going over proving triangular congruence by SAS, or the side angle side congruence theorem. Let's begin. So first things first, let's take a look at the definition of the SAS congruence theorem. The theorem states that if two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, then both triangles are congruent. So what that means is, if I have two sides of one triangle, let's say AB and AC, and both of these sides are congruent to two sides of another triangle, so let's say that DE is congruent to side AB, and that DF is congruent to side AC. And on top of that, the included angle of the two sides, or the angle in between the two sides, which is angle A and angle D, if those two are congruent, then by the SAS congruence theorem, by having one side, then an angle, then another side being congruent to one side, an angle, and the other side of another triangle, then by the theorem, both of these triangles are congruent. Now, before we look at an example, I want to go over three additional congruencies that would help you solve for the SAS congruence theorem. The first of the three are when two triangles share a side. So here I have triangle ABD and triangle CBD, right? And they're both sharing side BD. In situations like this, you can make the statement saying that side BD is congruent to side BD. And again, that is because they are sharing the same side. And the reason for that is because of the reflexive property. So again, whenever you see two triangles sharing the same side, they're congruent thanks to the reflexive property of congruence. The second of the three are when two triangles are connected by the same vertex. Right, so here we have triangle ABC and triangle DBE. Now, in situations like this, we can make the statement that angle ABC, right, so that's this angle here, is congruent to angle DBE, which is this angle here, right? So again, this statement is angle ABC is congruent to angle DBE, and they are congruent thanks to the vertical angle congruence theorem. The last of the three are when we have parallel lines, right? So line AB is parallel to line CD. Now, when we have two parallel lines that are crossed by a transversal, and that is this line here, line CB, when we have two parallel lines crossed by transversal, we can make a statement saying that the alternate interior angles are congruent, right? So what that looks like is this angle, ABC, right here, is congruent to angle BCD. So in our table, we can make the statement that angle ABC is congruent to angle BCD. And again, the reason for that is because of the alternate interior angles theorem. Great. So now with that out of the way, we can go ahead and take a look at an example. So here I have a quadrilateral that is separated into two triangles. We have triangle ABC, which I will mark here in yellow, A, B, C. And we also have triangle CDA, which I would mark here in blue. Now, we are given that side BC is congruent to side DA, which I will mark, which I will mark with these lines. And we're also given that side BC is also parallel to side DA. So I will mark that as well. Now we are being asked to prove that triangle ABC is congruent to triangle CDA. Right. So let's start with our table. And we'll begin by stating our givens. Right. So once again, our first statement would be that side BC is congruent to side DA. And for the reason, it's given. And we have our second given statement. Side BC is parallel to DA. And again, just like number one, second reason is that it is given. Now, in order for the SAS congruence theorem to work, we need three things, right? Two pairs of congruent sides and the included angle of the sides to be congruent for both triangles, right? So with our first given statement, we have our first pair of congruent sides. So we can mark that with an S. Now, all we're missing is the included angle and another set of congruent sides. So looking at the second given statement, it says that BC is parallel to DA. So let me, on the side, recreate that. So we have BC, that's the BC and AD. Both of these lines are parallel. Now, from the shape that we're given, I also notice that both of these parallel lines are crossed by a transversal. Now, if you aren't familiar, according to the alternate interior angles theorem, whenever you have a set of two parallel lines that are crossed by a transversal, then the alternate interior angles formed by the parallel lines in the transversal are congruent. So what that means here is that this angle here, which is angle BCA, would be congruent to the alternate interior angle CAD. So that gives us our statement number 3. Angle BCA is congruent to angle CAD. Right? So that gives us 2 out of the 3 statements that we need. We have a side, now we have an angle, right? And for the reason number 3, they are congruent because of the alternate interior angles theorem. So now that we have our S and our A, all we're missing is our final side. Now, if you notice from the shape that we are given, AC and CA are practically the same line, right? So both triangles share the same side. And through our reflexive property of congruence, we can say that side AC, so this would be our statement 4, side AC is congruent to side CA. Now that is because both triangles share the same side, right? And so for a reason, we would say that they are congruent due to the reflexive property of congruence. And that gives us our final side, right? So what do we have? We have one pair of congruent sides, which is our given statement, a pair of congruent angles, which we found using the alternate interior angles theorem, and a final pair of congruent sides, which was found using the reflexive property of congruence. Now, with all three of those combined, we can make our final statement saying that triangle ABC is congruent to triangle CDA. And the reason is because we have our SAS congruence theorem. And there you have it. That's a brief look at the SAS congruence theorem. I'm Daniel, and this is Preview Prep. Thank you for watching.